All right. Before I introduce myself, there are several routes that led to this talk, and one of them is this year's Olympics that happened here in France. And many of my friends just say, "Hey, it becomes so boring, so organizers need to, to need some special performances at the openings, or they need to show how people suffer from dirty water or whatever. But it should be much more interesting if we make all the legals, all the dopes legal. Let them boost whatever they want, so we will see real, superhumans competing without that game that someone is caught and another one is caught 2 years later, or sometimes it happens." Well, anyway, the idea is like, well, it's cool because we can make it legal for our applications. Nobody will blame us. So I actually contribute in OpenJDK, not that lot for the recent time, but I try. And the company that I work in is called Bellsoft, and Bellsoft does several cool things. The major one is Liberica JDK, which is an OpenJDK distribution, free and open source, and you can also have a support, a commercial support. And we realized that JDKs nowadays require good containers, so we started by thinking about how to do it right, and we came to having two more kind of things that we do. It's our own Linux, which is initially targeted only for containers, but it's just a Linux distribution called Alpaquita Linux, and our Graal VM distribution, which is called Liberica NIK, Native Image Kit. And we participate in the communities related to development, and mostly many engineers originated from Oracle. That's why we have appropriate experience for doing actual OpenJDK development. Well, another route for this talk is one of my previous talks, which is devoted to testing your performance, planning your performance and capacity, thinking about it from the development to production and support lifecycle. And what actually happens? It's still so true. We develop our applications. Developers are happy. Applications are developed by some specifications if they exist. After that, platform team says, okay, we need to run them in production, right? So DevOps help to continuously build and deliver that applications in production. So operations team, platform team manage containers typically, or at least we go there. But the chain is broken somehow because everyone's happy in that sequence of actions. But then the business comes, or FinOps eventually discovers that cloud spendings or just your lab spendings are way high. What happened? Well, I would say, as in a separate talk, right, one of the great reasons is just having your default Java options or empty Java options. That really happens. But the approach in general is to clearly define your objectives in terms of your quality of service, service level agreements, and define and track how you meet those expectations. And what indicators do you measure, how you try to fit into your requirements. And then we have two goals. We need to meet our service level objectives, and we have to reduce our resource consumption, to reduce our money spending, like in the most simple case, just spendings for our cloud instances. And we can reach two bad goals at once. We can spend a lot of money and we can still fail to meet our SLAs. And what happens is underutilization, right? And the same thing happens with our physical deliveries. But here, you see, the delivery is successful. We have delivered all that carrot seeds. It just wasted so much space, but they were delivered safely. The same happens with our applications, our containers. And at some days, we need really good performance. Or we spend too much money over some imaginable limits, which makes all our business efforts meaningless. So one of the approaches is horizontal scaling, right? And that other talk is about more about horizontal scaling, proper sizing. But it isn't always an answer. And even if we do horizontal scaling properly, we still can do vertical scaling, or we can do vertical scaling instead of horizontal scaling, right? There are, of course, some limitations that work for both of that approaches. And the major ones are related to our dependencies, to synchronization, to the points that doesn't scale. So that's the law. You have that non-scalable part, and that's just a constant in your capacity planning equation. So that's the famous application used, for example, not too serious performance tests here. Just we can make some conclusions on some comparisons on how we can containerize that application, how we can measure its performance, or how we have measured it previously. So some previous results in some experiments of the application. If we don't try too hard to scale it vertically, right, we can get some throughput from it. If we say, let's stay within some latency boundaries, the throughput will be like 5.5 K RPS, requests per second. That's just a number. That's a performance number in vacuum. We can also get some number for native images. Doesn't mean that much. And we can have some configuration for horizontal scaling within the same resources. So we can run an instance occupying the same overall amount of CPU, the same overall amount of memory, and it will show less, smaller numbers than the cluster that's running on the same machine, but just doing the right-sized horizontal scaling. And the cluster shows like 20K RPS. Good, right? But basically, we've done nothing with the application. And what's interesting in that experiment, if we try to run it on a very small pods, if we don't give JVM copies, enough CPU resource to run, it takes a very, very long time to start. It's impossible to wait for that application copies, that application replicas to start. So we can't get the final performance if the instances are too small. And that really happens in practice. So one of the big companies, they applied different optimization techniques. They finally got the solution as a service that tries to calculate and save their costs. So they deployed additional machines to their clusters, and that machines try to watch for how cluster works, to take some metrics. And afterwards, this solution says, hey, look, we don't need like 4 CPU instances, 4 CPU pods for that application. Just you can take 2 CPU ports because it only consumes 2 CPUs. But surprisingly, that commercial solution detects it's only on the long tail. Then the application has started and warmed up. And the operations team said, no, we can't do that. If we place, if we change the limit, and if we say we'll use 2 cores instead of 4, our application just doesn't start. That was a great recommendation. It potentially could save us 50% of money. Well, except it doesn't work at all, because the service doesn't work. But there are multiple ways where we can try to corner that problem. So, by the way, one of the interesting things here is a CPU boost for pods, though it requires a spare resource, a spare CPU resource on the node. But if you have it, it will help you, so you could probably reduce the instance size. So if you look at the containers and try to pack the application into a container, we can immediately see different how different and inefficient the resulting containers could be. So whoever saw a container like this, like from OpenJDK, oh, I'm not sure if I can make it larger. Yeah. No, that's a different plus, sorry. No. Okay, I'll read it. Okay, we take it from OpenJDK. I'm saying from OpenJDK latest. Is there a problem here? Yeah. Okay, latest is not a good choice. What else? Maybe. Right. You mean it's large? Okay, it's large, right? Yes, the best answer. I like that. You see, if we go to the web page, to that so-called default official image, we'll see deprecation notice written in large letters saying, please don't use this image as your base image for production. Never do that. I like the other answers too. Like it's a JDK, not Cherry, right? But sometimes it's okay. Mostly it's okay. And the exact version, etc. There are other things. Like here we copy the fed jar, right? And we can look at the resulting container image. Let's look. At least we can enlarge this one. Let's say this. 531 megabytes for a simple microservice. That's a lot. We actually don't need that large container images. Now, can we make it better? Right, first, in fact, in real, if we use Docker files or whatever build process, it's better to perform build using containers in any case. I just skip this part here. But there's a note saying, please don't do that. Do that. Here we can take the more optimal runtime, saying, in this case, Liberica runtime container, some exact version, some libc specifier. And also we can extract layers from the fed jar. So instead of doing that every time when we start the application, we can unpack them and use system class loaders. And what's also great, we have those layers as container image layers separately, which means when we update our parts of our application, and most typically we only update our business logic, we don't touch the libraries, we don't transfer that layers when we transfer new images to our pods. So it will transfer not 500 megabytes or 100 or 60 megabytes, but only a few kilobytes of code. We can also create a user not to run as root, right? And do some other tricks. But in the end, we'll just have some application. Of course, the interesting point here is to put some non-default JVM options, at least concerning your memory usage. Otherwise, you will waste most of your memory limit for your container. Because if it's not 80%, it's like max RAM percentage option. If it's not 80, like here, what it will be? 25. Yeah. Simple, but every time when I talk to people and they say, oh, yeah, you know, we fixed a big problem in our production, big performance one. And that's a great dope. You just give the memory that you already have. Please, JVM, eat it. And if we compare that the image size, we simply reshuffled the Docker file a bit, and we have it less than 200 megabytes with the full JDK inside. Could be made even smaller with JLink. All right, that's a simple part. And to make the images be the smallest ones, we brought the official port for Alpine Linux to OpenJDK. That's made by Pelsoft. But afterwards, we realized that Alpine Linux is not that great in sometimes. So we created Alpaquita as a replacement. It has libc version and LTS lifetime, whatever. Well, let's also study this application in a bit different way. So previously, numbers that I've shown were about getting the highest throughput with some latency boundary. We say, let's see when our responses, all our responses are below 100 milliseconds, what the best throughput we can get. Here's another experiment. Let's say we have a fixed rate load. That would be 1,000 requests per second. What resource consumption, what pictures we can get from that service? Well, here we can draw two things at once. We can draw memory consumption over time. So it's x-axis is time in seconds, and we only study like first 2 minutes of the application's lifetime, and that's a simple load scenario. We only ping the same endpoint, and we can study the CPU consumption, which is in red. So, is it visible? Okay. So it's memory in megabytes and CPU in percent. And 400% means that we consume 4 CPU cores or 4 vCPUs. What we can also measure is the response time. all the time that it takes to process the request. And that's a simple configuration for that application. It has an embedded database. All is very simple. Though, please see here what happens. It takes 41 seconds to warm up the application with this request rate. And if it would be a more realistic scenario in real life, what this time would be? How do you think? 15 minutes. Yeah, sounds realistic. So it can be not 41 seconds, but 41 minutes. It depends on your resources, of course, but yeah, 15, 20 minutes. That's true. And that's the thing that really makes us think about native images, right? Saying, hey, we can have it instant. But there are other options, in fact, like client VM. That's, by the way, that is used in Lambdas. The Lambda engine, like in Amazon, I think in other providers too. It uses client VM because it's smaller, it starts up faster, and it's very easy to use. We can compare the plots, how it works. For this particular application on this laptop, the startup time reduces slightly, but we actually did nothing. We just say, please include the client VM. We can perform that, for example, by using JLink or build packs that I will touch later. That's it. We don't change our application, but it starts faster and it warms up much faster. And the container is even smaller. We throw away 10 megabytes more just for free. Or we can apply native image. We can create a single binary, put it in a container, and the startup is instant, and we have almost no warm-up. We still have some initialization code running in the very beginning of the application, but not like the classical JVM case. But the peak performance is worse than the peak performance that we get with the server VM. It depends, of course, but that's the most frequent case. So let's look at the client VM. The overall picture looks kind of similar, right? We consume some CPU in the beginning, but not that much as the server VM, right? So here we need 3, 4 CPUs. Here we don't need it. So if we switch to client VM and we really want to, if we fit in our SLOs, now they can say, hey, your recommendations are feasible, but we also need to change that to save costs on our instances. That's just an example. Of course, client VM is not for everyone, but maybe for short-living or not so heavy-loaded applications, why not? And we also save some memory. So we can shrink instances in different ways. Just free, legal, dope. And we have this very, very fast warm-up. Yeah, we have slow first iterations, but by the way, they are not as slow as the ones with server VM, because we don't waste so much CPU for early compilations. And in fact, it turns out that the latency is not that bad in the very beginning, which also can help us to meet the objectives, surprisingly. And yes, with native image, one important thing that I forgot to start with is what happens in the very beginning here. What is this fall down to 0? That is how this performance test works. So we wait for the application to start. We just run the Spring Boot application and wait for it to be up and running. And only after it's up, actually after some delay, we start making our requests. So that's this 0 or almost 0 CPU consumption is we do nothing. The application has started, it's initialized, and we don't put any load on it. And then, so here, what's happened? Spring Boot has been initializing, classes were loaded, all that. Connections created, objects created, some garbage collections happened, some compilations happened, class loading happened. So we consumed a lot of resources. So we almost don't do that here with native image. You see, it's a small peak. It still exists. But here's a long pause because we wait for the same timestamp to start having the load. And you see we consume, in this case, we consume less memory, but we actually can control that by some options again. Use your memory as a legal dope for your application, for your JVM, in this case for substrate VM, to let it breathe, to let GC work more, to let it work easier. And yes, again, we can replace four vCPUs by 3. Well, finally, we don't have any initial peak in latency. We have the best latency from the start, though it's not as good as with warmed up applications if we trans on the server default server VM on hotspot. Well, what else we can use here? That very initial part related to class loading. We load same classes for the application, for every replica. But after we have loaded the classes, we can dump that loaded class data. And we can reuse it. So we can perform that when we create our container. If we know our target environment, if we know or approximately know limits, we know the application, we can create that shared archive with class data, memory map it with every replica. And we will speed up the startup our application. We can reuse that archive because it's shared memory data. And let's look on how it can look in our Docker file. So you see we had, that's why I need that tiny font, right? Because it can become longer. In that Docker file, we still have all the layers we unpacked. We can create a layered image, multi-stage build here. At first, we say, please run our Spring Boot application in a special mode. And the special mode says, well, exit on refresh when the application has started, in fact. And also, please archive classes at exit. And we say, provide the path in our container image where we save the archive of loaded class data. Now it's in our resulting image. And we basically say, hey, in entry point, please use that shared archive file. And by the way, oh yeah, I haven't lost the max RAM percentage setting. Nice. Yeah, what else is here? And in the previous example is in runtime, JRE is used, not JDK. Let's check what happens if we have it advanced CDS. So simply advanced container image was below 200 megabytes. An advanced image with class data sharing is 305 megabytes. So we've spent some disk or network traffic for that shared archive, but it provides us better startup. That's a trade-off. That's a legal dope. We haven't changed the application. Spring does that for us, does some of it for us. JVM does that for us. We do nothing, only write proper Dockerfile, proper configuration, or just a property. Well, one more route for the origin for the name of the talk is crack, which is not a drag, but a checkpoint and coordinated restore at checkpoint. We can take our application when it started, when it has done something, and use Linux mechanisms to freeze it, to say, hey, let's create a frozen version of our process, which we can restore at any time, like Han Solo. But it's better than a frozen Han Solo, because we can restore multiple replicas of it. Though there are also special actions to take when we restore replicas, because they must not be entirely identical. Otherwise, we'll have some security problems. But it has been solved. Though you need a special JDK version. A JDK that obviously supports that crack technology. Crack is an open JDK project. There are open JDK providers like us that offer such builds. Initially, Azul was the first. They created the implementation based on Creo, and now it's in OpenJDK, and any provider can offer their builds. So if we compare, again, the initial variant with server VM and the one with CDS, I would say let's measure in fingers. So here we have this long startup, right? And that tall. And here is much thinner, visibly even in such plots, right? We have longer gap here when nothing happens. It has been initialized. We need much less memory when we do that, because we just memory map. We don't waste, we don't perform all the service actions that JVM needs to perform to create classes, to do mallocs or whatever. Nothing of that. We just have ready-made internal structures. The CPU consumption is about the same, but you know, the tail picture is similar, right? We got the same application, and we do it only by JVM means. And also we have Spring Boot helpers to make it easier for container creators to get those containers. And if we look at crack usage, it's trickier. So I would say the central part here, we can't create a non-root user in that container. We actually need to be the root inside to invoke all the special functionality required for crack. We still can have that thin jar layered image. It works, finally. We need special JDK for the build. We need special JRE to run the application. It has, in this example, it's Liberica runtime container, blah, 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 crack, and also slim muscle, whatever. By the way, are there any questions? Okay. And the second, and maybe the most tricky part, is that we can't effectively perform all the required actions within or during the regular Docker build. There are two ways of creating containers that require privileged steps during the build. And checkpoint is the privileged step. one way is to use buildx and special privileged builder and also some workarounds to make it run. But I would say the most simple way so far for now is to have a small script that creates at first creates a special image that is used for checkpointing, and then creates another image based on that. The image that will be started within all the replicas. So what happens here? We say the entry point of the resulting image. Again, we will perform a different action. We will not exit on refresh, but we will checkpoint on refresh. So that's a Spring Boot dope. Spring Boot, since version 3.2, supports crack as well as CDS. So it can help us to create the instantly starting copy of our running service. And we say, hey, crack checkpoint to this running container file system. We also can provide some memory options, and we have the same launcher. And what will happen when we start this container? It will start the application, it will checkpoint, and actually it will exit. But in that service script, let's not shut down the container when the process has finished. So it will be a running container, a living container, with the checkpoint in its file system. And finally, the second step is to commit that running container into a new container image. That container image will contain the checkpoint in its file system, and we alter the entry point, saying, please start from that safe checkpoint. Java, start from this checkpoint. We don't need all the previous arguments, like where's the, what's the main class, whatever, because we just make our previously frozen application running. That's what happens here. And it will have a new name. And yeah, we actually don't need the capabilities when we run the resulting container, but we need special capabilities when we create the checkpoint. So if you do that in a cloud or in a managed Kubernetes, it should support it. It must support these capabilities. Okay, is it? Well, too complicated? First of all, what's the container size? So there are multiple containers. The first one is called just checkpoint, the service intermediate step, the one without the actual checkpoint. It is used to create a checkpoint. So it's more or less similar to what we have in CDS. And when we have created the checkpoint, we have spent additional 200 or almost 300 megabytes for the checkpoint, because it's an image of a running process. It also contains heap, it contains JIT compiled methods, everything. Though, well, we spent the disk because we have spent our memory for that. But the benefit of having spending the disk and network traffic is instant start. And in that instant start, we don't waste the CPU. We don't need additional threads in the beginning of the JVM lifetime. We only need to memory map the process image file into memory and to perform some small service actions. So it's very effective. We can greatly reduce the CPU usage. Though you still see some warm-up, right? Because we only cut off that initial part entirely. So that's the part before this gap. We have cut it off. No waste here. But we still have that additional warm-up. We can check point later manually here at some of these points, but we must need to know where. And the state must be consistent, so it's harder. That's why Spring Boot only offers us that convenient option for that point, not for later points. Because here it's a known state for every Spring Boot application. Here we must look from the application's perspective when to checkpoint. We also can save some memory here, by the way. You see the crack restored one consumes less memory, right? Because we don't need some allocations, service allocations that happen in a normal JVM run. Nice bonus. 3 dope. All right. When we plan the capacity, probably finished with those examples. We just need to remember about all of our service level agreements, some formal or objectives, right? Some related to how service responds and also how it's been used by platform team. And also, yeah, the thing here relates to the CPU behavior and scaling on different CPUs. All right. Multiple times I mentioned memory settings, providing right heap size, right tuning for the memory. And also that means tuning for your GC. Because with default ergonomics, your GC selection depends on the amount of memory and the amount of CPUs that you have, but you of course can change that. And then the major question is, what's your target metric? What's your primary goal? What you're trying to optimize? If you're trying to optimize latency, which is probably the toughest thing we do, right? We now have great tools. We have Shenandoah for many releases since Java 11. And there are even Shenandoah ports for 8. And now we have generational Shenandoah. Why do we need generational Shenandoah? And why do we need that Gen Z? Why do we need generational collectors? Because we want to collect generations separately. Or maybe it's better to say and. We want to save memory. Because generational collectors allow us to perform young collections. Well, we have young generation, typically. And that helps us to lower the amount of consumed physical memory for our heaps. Because we collect them quickly and almost entirely, right? It's young generation, young objects, and they die fast. And they all go away. So initially, the trade-off that was by design, right? That was, okay, let's do that. Let's make a good low latency collector, but we can sacrifice memory consumption. We can sacrifice footprint, but we will have very short pauses. That's how Shenandoah and ZGC started. But now, or soon in the future, we'll have them both. Consuming not too much memory and providing you very short pauses. That's legal and easy dope to use. You just switch to a new garbage collector. And by the way, you have less settings for your garbage collection. Like for ZGC, what's the number of settings that you typically should apply to your running application? 2 or 1. So it's the size of the heap and the number of threads. And there are defaults for both, and defaults for threads is, in most cases, works good. Also, less settings in Shenandoah if we compare, for example, with CMS, who remembers tuning CMS or tuning G1 in Java 8. Now we have much less settings to tune because ergonomics work much better. We still have parallel GC that we can use for throughput critical applications. It's still the best. Recently, like maybe 2-3 days ago, AMD announced their new CPU, a big beast, many cores, and server vendors actually announced real server hardware based on that. It's called Titan. It's funny, if we look into their spec JBB submissions, I think it's still parallel GC. There are not too many settings, but well, it's impressive. Because it's still the GC that provides very good latency and throughput in that benchmark. That sometimes corresponds to many real applications. All right, we can also get higher throughput from G1, from default garbage collector, just by relaxing the POS requirements. And if we need to save memory, right, we can simply use smaller instances, not too many cores, stick to serial GC sometimes, or just relax the time ratio for G1. And of course, we have all the different tricks and many settings that we can apply, like the object alignment, and huge pages, etc. Now, these are DOPs we just get for free with new JDK versions. Just don't forget to try them. Get those potential improvements, try them with some performance testing frameworks that you use for your applications. Get results, say, hey, we can save something when new JDK arrives. Well, obviously the process is quite straightforward. And the main setting is still, but maybe it's not forever, is the amount of Java heap that application will use. And to determine the amount of Java application, amount of Java heap the application needs, what do we need? We need to experiment. We need to see what resources it actually consumes, or we need to make a good guess. Or we need to do both. We can make a good guess. We can later, when application finishes, analyze what resources it has consumed and make a better guess. In typical web service, there are multiple well-known points that consume your native memory. And all besides native memory can be used for your Java heap, or almost all of the memory that's available for the pod. So the idea to calculate good guess based on that known points led to having JVM options calculator or starter in Spring Boot build packs. So if you use build packs for your Spring Boot application, you can create containers without writing Docker files. You can use cool features like CDS just by setting an option. And you can even have alternative variants. Like we have created a build pack based on Alpaquita and Liberica Lite, which consumes less memory, and you get it for free. You only change or provide one property in your POM.xml file, and you have less resource consumption. I had it somewhere. Yeah, maybe we can open. Where is it? Probably it's in POM.xml. Let's try to find it. Okay. That's for zip. Yeah, I think that's, yeah. That's the only line. That's the easy dope. You just change one property in POM XML and you get container that consumes less memory. Whoever tried build packs? Cool. Because just check how it works. You say, hey, Spring Boot, please build an image for me. And you get a container image in your repository. And when that container image starts, it calculates memory settings for your JVM. So it effectively uses resources provided, and it does it in runtime. So if you enlarge your ports, you get different memory settings for Java running there. So it's easier to use. Another cool thing is that you switch between classical JVM and native image by using only one property in that command line. You say, hey, use profile native. And you get the container that contains native image. Though your build time increases, but that's the only difference. All right. Things that I mentioned. First of all, the JVM thread count, or expected, right? And the main source of that many threads in a good application is, I can ask because it's written in small letters here, is your application server. Because it has a thread pool to handle to process your connections, your incoming HTTP requests in classical model. And it can't create an infinite number of threads or thread per connection because every thread has a stack. If it's a real platform thread, it requires 1 megabyte or half of a megabyte of native memory. And switching between those threads, managing a lot of real threads, is heavy for your operating system and for your JVM. So it simply works slowly, or you get out of memory, or you get some other unpredictable things, and you don't have that bound. So we must take into account how many threads do we have. We must have some headroom. All classes require native resources like native memory. And of course, there are other sources. Well, I already mentioned that build packs help here, but let's try to think about avoiding other nasty things, like all that thread limitations or maybe something else. You saw that AUT is not inconvenient, right? You have some concepts and you only work with class data for now. But there's a new project in OpenJDK called Project Leiden that's targeted, that aims to condense more things into shared archives. Not just class data, but also your compiled methods, also other things that are initialized in the same way in every replica or in every application iteration start, right? And there was, or there still is, a JVM implementation that does many of the things, which is OpenJ9, that has class cache. It also caches some compiled code. And now OpenJDK gets quite similar workflow, or at least in that Leiden project, it gets quite similar workflow to OpenJ9. We can cache some things during the run, right? And there are just modes. What do we do? It's a default mode, which is that also has the text constant. I don't remember one. We can create the shared archive, or we can use it. So obviously, here's a list of things that we can reuse between runs. But let's rewind a bit what we saw with that CDS archive. What do we have now? We already can store some class data. But how portable it is? It is portable, but not entirely portable. If you have changed class path or different class path during start, it won't work. If you change some JVM options, like pointers compressing mode, it won't work if you don't have an archive suitable for that mode. Some other platform-specific things can make your archive non-functional, or your JVM trying to use that archive. So you must create it in an environment very similar to your plant production environment. But probably if you change it only a little bit, it will still work. If you save, yeah. That's a good question. You need to try that. Yeah. I think it should, yeah. Because you obviously can transform all the classes all the way, and you can't compare what do you have. So if you store JIT compiled code, or especially AOT compiled code, the code is compiled for a specific platform. And that specific platform means the exact set of CPU features available for instructions that you can actually use. And if you change your CPU and you restore on an instance that doesn't have some extension that you have used in your code, what will you get? You will probably successfully restore your application, but you will get a SIGIL, and when method is called, which contains a compiled code, if you have compiled code for that method, and if this compiled code has an instruction that's not present in your actual CPU, Linux will say, hey, our processor is not capable of doing that. So that's a danger here. And of course, you also waste extra space. On top of that CDS data, you can store that code cache, etc. But surprisingly, it's not a huge amount of memory on top of the CDS data. All right, that's how we enlarge resource usage, right? Or something. Can we make it smaller? Another great project, or another dope, is Project Lilliput. Also developed in OpenJDK. And what's made smaller? What becomes a Lilliput? Here's a hint. That's the size of an object's header in OpenJDK. So if you have an object having no fields, 0 object, right? It still contains 12-byte header. Or if it contains like 1 byte, you still need to spend a lot of just to be capable of performance synchronization using that object as a lock, or to use it in identity hash maps, or to perform proper garbage collection involving that object. Surprise. But the good news is that that number can be made smaller, which practically leads to great savings in applications. Like up to 20% of their footprint could be reduced, could be wiped away for free. You just say, hey, JVM, please use compact headers. 20% heap off. Nice dope. You can try some, well, I'm not sure about preview builds, but Lilliput version 1 is close to be ready. So it's a thing coming soon to OpenJDK. You see, it's an open job. So very great work by Roman Kenke. And he also said that the version 2 is planned, which will have even smaller object headers, though it will require special logic for every garbage collector to work properly. So it's a tricky dope, but again, free for us as application developers, as users. We just say, hey, please use even smaller headers. Okay, we can use that. So finally, what to do with that threads wasting native memory? Well, let them be not platform threads. It's easy. We now have virtual threads, and Spring now supports virtual threads. And Tomcat supports, and Netty supports them. So we can simply enable virtual threads and get unpredictable behavior with our old applications because we have enabled virtual threads and application doesn't know how to balance its resources with this new situation. However, it's a solvable issue. And we need newer JDK. Though, we don't have that dependency anymore on max threads. Cool. So, threads overheads, solved, provided by free. Just take the dope, make your application work more effective in a sense that it can use some CPU that it hasn't used before, right? If you already have your CPU used properly, it won't be better. If you still have locks, if you still have improper synchronization stalls, it won't be better. Again, if you have a memory leak, you have a memory leak. But if you have used huge heaps and experienced long latencies, you now can have humongous heaps and very short latencies. Sub-millisecond latencies. That's what I've observed with real applications, and you just switch it to ZGC, give it more than 100 gigabytes heap, and you still observe sub-millisecond pauses. Wow. That's convenient. But all things are great, and especially on conferences, we talk about different new stuff, and people come and say, oh, that's so interesting. We are on JDK 8. Who's on JDK 8 and 11 still? Yes, you have the real production. Because why do we have to migrate? We don't have to. Business doesn't have resources. Business doesn't want to change things that work, right? It's engineering, it works. Don't touch it, don't migrate it. We can have a better performance. Wow, that's a different situation. We have new requirements. We have an old application, and we would like to perform it to perform better. We would like to consume less resources because it's too expensive to have one. But from the other hand, well, we need the original team probably that created the application to migrate it properly, because we have dependencies. We have old libraries that won't work on newer JDK versions. So we started from a simple idea. Okay, we can make some LTS JDKs slightly better for the cloud. That's how JDK Lite started. We can make it smaller, We can have additional performance backports. We can have additional feature backports, such as muscle support to have small containers. All right, but that's not enough. For the case that we have legacy applications that do need those new dopes that only exist in newer JDKs. That's how we created our Fuse JDK. It's called Liberica JDK Performance Edition. And the idea is very simple. For your application, it looks exactly like JDK 8 or 11. For all your libraries, your class libraries, JDK 8 or JDK 11, you have same APIs. It reports as, okay, I'm an old JDK. But inside, internally, it uses new JVM. Currently from JDK 17, but likely it will have JDK 21 soon. And you get that cool new dopes for your Java 8 and 11 applications. And the famous target is Spring Boot 2.7x, right? Which is very widely used, and it's not migrated often. And there are great features. Not all the features can be ported from newer JDKs to that fused ones. But some cool features can be ported. Like I personally like ZGC. Currently, only non-generational variant is available in Performance Edition, but well, it's still an option to go if you need to get the lowest latency possible. And other things like faster ZLib, intrinsics, etc. And it works very well in some industry known benchmarks. In real applications, we have seen some like 15-20% speed ups. So here in benchmark that simulates some application, we have times speed up, which is very impressive. And latency, if we switch from G1 to ZGC, it's just a different quality for your existing application. Right. So there are some different parts. And I already mentioned Spring Boot 2.7, which is a widespread version. And often we see applications running on 8 and 11 with exactly this Spring Boot version. So we can lower the latency for such services. And also footprint. All right. I hope that was not the overdose of all the dopes. Yeah, we had some overview. There are many more of them. I just selected some voluntary, saying, hey, these are easy ways to improve our productions. Easy ways. Just build your container slightly differently. Just put some simple options. You get savings. Right. Let's do it. Questions? Yeah. Thank you. Yeah.
Regarding to CDS and Crack, you mentioned using that with Spring Boot-based apps.
Yeah.
What would it take to do that with non-Spring Boot apps?
Yeah, definitely. So Quarkus should support it as well. And you can simply create an application without using any framework and use that features. So for to create your crack checkpoint, there's a JCommand diagnostic command that you can issue to your running JVM or container, and it will create a checkpoint. When the checkpoint is created, the application exits, and you get the cryo state. With CDS, this option is with us since Java 9, and then it has been backported to Java 8. So it was a commercial Java 8 feature, and then now it's an OpenJDK 8 feature. You just create the archive.
That's it. No change to the app, whatever.
Yes, yes. I just like Spring Boot because Liberica is the default runtime for Spring Boot containers for build packs. Yes.
Which are the dopes you purposely avoided to mention because they are way too complex to use?
Well,
the ones where you advise to avoid.
Obviously, we most often tune GC. There are a lot of G1 settings and other collector settings you can just try to explain and try to figure out scenarios when we have best combinations for that. So that's the number one. All the GC flags.
Thank you.
Also, we can tune the compiler heavily. If you really depend on that, you can make your methods to compile with much better quality. Some interesting prototype that we have created. We met some problems on different platforms when the amount of compiled code in code cache, the JITed methods, was very big. We had performance degradation for those methods' performance. And it turned out that you actually have to place your hot code properly, compactly, to have the right performance, the best performance for your hot code. The code is the same, but the performance depends on the placement. So the thing that we have created is an agent and a special set of special tricks in the JVM itself. And the agent profiles the application and collects your hot code, or instructs JVM to collect your hot code in one special place, which is compact. And then it improved the real performance of your application. But again, without changing the app itself. You just need a special JVM. You need some couple of settings, probably even just one setting, and special agent, which attaches dynamically. That's another example.
Okay, thank you.